Hello, seniors. Continuing with yesterday's class, today we're going to see the demonstration for the derivative of natural logarithm of x. Okay, natural logarithm of x. Remember that this demonstration, just to remember, yesterday we've seen the demonstration of the derivative of e to the power x. We've shown that the derivative of e to the power of x is the same function, e to the power of x, right? And today we're going to show why the derivative of natural logarithm of x is 1 over x. And remember that these demonstrations, you don't need to know them, okay? I'm just showing you this for you to understand where this comes from, okay? So this is what we're going to do today. We're going to demonstrate that the derivative of natural logarithm of x is equal to 1 over x. Okay, so to start with this demonstration, there's a definition that you should know, which is the value of e, which is Euler's number, okay? If you remember from last year, when we studied exponential functions, we've seen where this number comes from. But just to make a quick review, I'm going to show you where this comes from. And if you have your calculators with you, I strongly recommend you to follow what I do in the calculator to understand this better, okay? So, the Euler's number comes from a financial, well, it has a financial application, and basically if you remember the compound interest, it follows this formula, okay? 1 plus 1 over n to the power of n, okay? And basically what we're going to do to get to the value of e is try evaluating that function, f of n equals 1 plus 1 over n to the power of n, for different values of n, and approach the value of n to infinity, okay? And we'll see to what value this converges. So let me show you the calculator. So you should be able to see a calculator right now. So if you're looking at the calculator, we're going to go, first of all, we're going to go to menu table, okay? Menu table. And let me erase all of this. Erase. So we're going to plot the function that we're talking about, which is parentheses 1 plus 1 over x, remember we're writing x instead of n, 1 over x to the power of x, okay? To the power of x. So this is our function. If we go to set, before going to table, remember we want to give very big values of x to this to see how it is behaving. So we're going to go to set, F5. We're going to give it start at this number, 1, and end at this is 100,000, okay? I'm just writing a big number in order to be able to see what's happening, okay? And the step, you could give it 1,000, for example, okay? So if we go back, after setting this, we're gonna click on table, which is F6, and you'll see what happens. So for x equals 1, the value of the function is 2. You see that here, the third column is the derivative of the function, but we do not care much about this for now, okay? This is now being displayed in the calculator because remember you activated, we go to shift menu, you activated derivative, right? That's why the table now is showing the value for the derivative. But we don't care about this column for now. We're just looking at the value of x and the value of y. So what do you notice? As I am increasing the value of x, you see that the value of the function is converging to a value, right? 2.716, 2.7176, 2.7178. So you see that the value of y is changing by a little bit, while this values of x are increasing by 1,000, right? So you see that we are converging to a value here. Down here you can see with more decimal numbers. And you see that as x increases towards infinity, right, as x is increasing towards a really big number, we see that the value of y is converging to a value. It's remaining 2.7182 and so on, right? It's converging to a value which by definition, let me go down up to the last number. You see that the decimals are changing just a little bit right now. So if we get to the last value, which is somewhere around here, there, we get to this value, which is still not the perfect value, because we can keep on increasing this and get a more approximate value. But if you notice, this value by definition is what we call Euler's number, okay? If we go to menu 1 and we write let's put to the power of 1 to get the value of e, you see that this is exactly the value to which we were converging, right? 2.71828, and so on. This has more decimal places. But this is what we define as Euler's number. If we see this situation graphically, let's see. Let's graph this function. Let's click on draw. You see that, okay, we're only looking at the positive values because the value of n should be a positive number. So you see that this function it has a horizontal asymptote, which should be y equals e, right? The converging value is Euler's number. So let me plot the horizontal asymptote, which would be y equals e, okay? So y equals e, I'm going to put to the power of 1 just to make it e. So if we draw this, we should see a horizontal asymptote, which is exactly what you look there. A horizontal asymptote at y equals e. So the blue function, although it looks like it touches the red one, it never actually reaches it. It is a horizontal asymptote. So that's why we define the limit when n tends to infinity of 1 plus 1 over n to the power of n equals e, okay? Euler's number. So let's go back to the electronic assignment. So this is why, by definition, e is the limit when n approaches infinity of this function, 1 plus 1 over n to the power of n. I wrote this table here to the right just to let you remember why e is equal to the limit of this function when n approaches infinity. Okay, so with that definition, we can make the demonstration. So let's start by remembering the definition of a limit. Of a derivative. Here we wrote the definition of the derivative, which is f prime of x equals the limit of f of x plus h minus f of x divided by h as h approaches 0. Okay? So from this definition, let me write this a little bit better. There. So from this definition, we're going to define, first of all, f of x. In this case, f of x, we want it to be natural logarithm of x, so natural logarithm of x. So f of x plus h would be equal to the natural logarithm of x plus h. Okay? So now we can apply the definition and say that f prime of x is equal to, remember the definition, the limit when h approaches 0 of f of x plus h, which is natural logarithm of x plus h, minus natural logarithm of x, which is f of x, divided by h. Now, if I try substituting the values of h with 0, I should get an indetermination. So let's see. If I replace the values, I'll get natural logarithm of x plus 0 minus natural logarithm of x divided by 0, right? Natural logarithm of x plus 0 is the same as natural logarithm of x. So natural logarithm of x minus natural logarithm of x is equal to 0. So this is equal to 0 divided by 0, which is, as you know, an indetermination, which we need to solve. Okay, so how do we solve the indetermination? To solve the indetermination, we need to remember some laws of logarithms. One law we need to remember is that whenever we have a subtraction of two natural logarithms, natural logarithm of a minus natural logarithm of b, this is the same as saying the natural logarithm of a divided by b, right? And the second law is that if I have natural logarithm of a to the power of k, I can take down the k and write it in front, right? So a natural logarithm of a to the power of k is the same as k times natural logarithm of a. And also the inverse property is can be applied, right? If I have this, I can take the exponent up here and rewrite it as this, okay? So given those two laws, what I'm gonna do now is, you see that here we have this abstraction of two natural logarithms. So I'm gonna apply this first law over here in order to rewrite this as a fraction. So if I rewrite this, f prime of x would be equal to the limit when h approaches 0 of natural logarithm of x plus h divided by x. I'm taking this dividing now, divided by h, okay? So I can take this exponent, let me see, yes, I will separate the division and I will rewrite this as the limit when h approaches 0 of 1 divided by h times the natural logarithm of x plus h divided by x. The only thing I did is take this division, which was down here, I brought it up to the front, and it's the same thing, okay? So why do I do that? Because I want to take this now to the exponent, right? Applying this property over here. So if I rewrite this expression, this is the same as saying f prime of x equals the limit when h approaches 0 of natural logarithm of x plus h over x to the power of 1 divided by h. Okay? So to the power of 1 divided by h. There you go. What I did was take this to the exponent, basically, applying the second law of logarithm you see to the right. Okay, so why do I do this? What I'm gonna do now is, before actually showing you the next step, I'm gonna separate this division, and I'm gonna write x divided by x plus h over x, okay? So this is the same as saying the limit when h approaches 0 of the natural logarithm of x divided by x is 1, so this is 1 plus h divided by x, okay? I just separated the fraction into two different fractions, okay? I can do that. So this is to the power of 1 divided by h. Okay, once I have done this, I need to do something that is called a variable change. Here we're applying something that in Spanish is called an artificio matemático. And we do that in order to be able to solve the limit, okay? So I'm going to make what I told you something called a variable change. So I'm going to write it. Let's see if I have space here. Variable change. The variable change implies the following. I'm gonna call h. I'm gonna call this x divided by n, and you will see why in a second. Okay, so you see that h is the inverse of n, right? So if n approaches a very big value, what will happen to h? We're dividing x divided by n, so if n approaches a very big number, then h will approach 0, right? So by knowing this, you should know that if h is approaching 0, just as we wrote in the limit, then that means that n is approaching infinity, okay? If this is a very big number, then this will approach 0. So, given that information, and using this expression we just wrote here, we can say that if we reorganize this, for example, if I take the x dividing down here, I can say that h divided by x is equal to 1 over n, and also that 1 over h is equal to n divided by x, right? If I flip this and write 1 over h, this is n divided by x, okay? It's a way of reorganizing this. Okay, so why did I do this variable change? In order to be able to replace these values, if you take a look at here, here I have h over x, right? But I rewrote h over x as 1 over n, which is what I have here, okay? And the second variable change I did, the second reorganization of the variable is for this 1 over h we have here. 1 over h, according to our variable change, is equal to n divided by x. Okay, so that's why I did this. So I can rewrite and pay attention at something. If h approaches 0, I'm going to do this with green. If h is approaching 0, if I'm changing my variable to n, because I'm going to be working with n now, I should pay attention at this. Now n is approaching infinity instead of 0 as h did. Okay, so taking into consideration all of those changes, we're going to rewrite our limit as the following. We're going to write limit. Now we're focusing on n, which is approaching infinity because of the variable change we just did, of, we're right here, right? So of the natural logarithm of 1 plus h over x, its equivalent is 1 over n, right? So I'm going to write 1 over n to the power of 1 over h, and its equivalent is n over x. So this is to the power of n divided by x. N divided by x. Okay? So now, if I take this x down here using properties of logarithms, this is the same as saying the limit when n approaches infinity of 1 divided by x, 1 divided by x times the natural logarithm of 1 plus 1 over n to the power of n, right? And you know, before doing this, I can take this, since we're looking at the limit when n approaches infinity, I can treat this as a constant number, so I can take it out of the limit, right? So this is the same as saying 1 over x times the limit when n approaches infinity of a natural logarithm of 1 plus 1 divided by n, 1 divided by n to the power of n. And we know that by definition, this expression is e, right? Sorry, without the natural logarithm, this expression, if we take it to the limit where n approaches infinity, is equal to e, right? So this, I can take out the natural logarithm outside of the limit and rewrite this as 1 over x. So f prime of x, we're always talking about f prime of x because that's the objective, find the derivative. So this is equal to 1 over x times the natural logarithm of, and I'm going to write this with brackets, of the limit when n approaches infinity of the natural logarithm, of 1 plus 1 over n to the power of n. There you go. So this is, and let me highlight this. This is what we defined as e, right? According to this definition over here. So if that is e, let me write that here. This is e by definition. So finally, we're finishing with a demonstration. The derivative of f of x is equal to 1 over x times the natural logarithm of e, right? Instead of all that thing. And if you remember from the definition of logarithm, the natural logarithm of e is equal to 1. So finally, we can conclude that the derivative of the natural logarithm is 1 over x. Okay, all of this process was done just to demonstrate what we have in our formula booklet, which is basically that the derivative of natural logarithm of x is equal to 1 divided by x. Let me show you the formula booklet just to let you know that you have both derivatives here, right? So that we have the derivative of e to the power of x, which is e to the power of x, and we have the derivative of natural logarithm of x, which is 1 divided by x. So as I told you, you don't need to know these derivatives by heart, and you don't need to know all of this demonstration we just did. I'm just showing you this for you to know where this comes from. Okay? And you have both of these formulas available in the formula booklet. Okay? So, let me write that here. Both derivatives are in the formula booklet. Okay, so just to finish, I want to finish this video by doing some examples about how we apply these new derivatives that we've learned yesterday and today into problems, okay? So let's solve the first exercise, part A, which says, find the derivative of each function. So in the first case, we have f of x equals 3 times e to the power of x. Okay, we know that the derivative of e to the power of x is e to the power of x. So in this case, the derivative f prime of x is directly 3 times e to the power of x. Remember that the constant number in front does not change, okay? We only need to differentiate this expression over here, which its derivative is the same thing. So the derivative function is the same thing as the original function in this case, okay? So this is the answer for the first part. Then we have part B. I'm going to separate this. Part B, f of x is equal to x squared plus the natural logarithm of x. Okay, so how do we find the derivative of this function? X squared, we already know it. We follow the power rule to differentiate this, and this would be equal to 2x. And now we know how to differentiate natural logarithm of x. The derivative of natural logarithm of x is 1 over x. So this is plus 1 divided by x. And this is the result. Okay. Finally, for part C, the function f of x is natural logarithm of e to the power of 3x. Okay, so in this case, before we differentiate, I see that we can, by applying laws of logarithms, we can take this exponent down here and see what happens, right? So we can rewrite this as f of x equals 3x times natural logarithm of e, right? And we know that natural logarithm of e is always equal to 1. So basically, what we're finding here is the derivative of 3x, right? And the derivative of 3x, you should know already that this is equal to 3, right? And this is the result for this exercise. So these are some simple and easy applications of these new derivatives that we've learned today. But we're going to practice later on with more exercises about this. But you see that this is very mechanical in its applying formulas, and that's it. Okay? So I hope this was clear. I know this was kind of a tough tutorial video. And as I told you, you don't need to know these demonstrations, but I just wanted to make sure that you understand where this comes from. So I hope it was clear enough, and if not, please let me know your doubts, and that's it for today's video. See you, senior.